Hello, today we will talk about vectors. We're going to start with 3D name vectors. I know this is a little bit of a silly example, but it drives the idea of vectors. So a 3D name vector would be something that contains three names, say Mabel, Betty, and Dorothy. Whenever we write in a three-dimensional vector, we want to make sure it is that it is clear which one the first name is, the second name, and the third name are. In other words, implicit in this notation, we have that Mabel is first, Betty second, and Dorothy is third. If we rearrange the names, then we have a different vector. Say we put Dorothy first, Dorothy, and then Mabel second, and then Betty last. Well, that is a completely different vector. That is not the same vector. So again, implicit in a vector, we have to have well established the order in which the elements of the vector are written or are placed. So again, in this second vector, Dorothy is first, Mabel is second, Betty is last. On this first vector, Mabel is first, Betty, and Dorothy. All right, so this is a three-dimensional name vector. We could have vectors containing any kind of elements. So for instance, we can have a 3D furniture vector. So in this case, we could have, say, a chair, a table. That's a table. There, looks a little better. And again, a chair. So we could have an element repeated in more than one place of the vector. So up here in the name vectors, we could have Betty in two places or in three places. Here we have the chair in two places, in the first and third. So the table is in the middle. This vector is different than the vector which would cast the table first and then the chairs last. So that is a three-dimensional furniture vector, two of them actually. And by the way, if we have this kind of setup with two chairs on a table in a three-dimensional furniture vector, there are three different ways or three different vectors we could write. The table could be first and then the two chairs last, or the table could be last and then the two chairs first, or the table could be in the middle, as in that case. With three different elements, such as up here with Mabel and Betty and Dorothy, we could have 6 different vectors. While here we can have 3 different vectors using 2 chairs and a table. Now, if we have 2 tables and a chair, then that is another set of 3 different vectors. That could create another set of 3 different vectors. All right, but we're going to talk about 3D real vectors. Actually, what we mean by that is real number vectors. Real number vectors. You could have, as I showed you earlier, any kind of elements in a vector. You could have furniture, names, whatever. But we are going to be using only real number vectors right now. So the elements in a vector could be any real number, say 2, -7, 5. And that means that this vector contains the elements 2, and it is clear that 2 is the first element, -7, which is another real number, and that is the second element in the vector, and then 5 is the third element. We also call those elements components. Components, first component, second component, third component of the vector. So there is a three-dimensional vector, real vector. Usually we don't say real number vector. It is understood that when we say three-dimensional vector, so 3D vector, we mean a vector whose components are real numbers. As a matter of fact, oftentimes we don't even write down 3D because it is understood here in this notation that we have 3 dimensions for those vectors. We could have a 2D vector, 2D vector, and that would, an example of that would be 2, -7. Please do not assume that this vector is part of that vector. That is not true. Those two are completely different objects. This is a three-dimensional vector, while this is a two-dimensional vector, and they are not, one is not part of the other. They're not related. They live in different countries and different planets. They're not the same. Even though this one has a 2 and a -7 and a 5, and this one has a 2 and a -7, which makes them look very similar, they're not the same. The same thing happens when we use letters. You know, you have a generic X, Y, Z vector, which is three-dimensional, versus an X, Y vector, but those two are not in the same planet. They belong to different sets. Yeah, one could say, well, couldn't this be embedded? The letters are misleading. Can this be embedded in that? How are we going to put? Are those two going to be the same? It's not clear how we're going to embed one into the other. We can make a projection. There is what is called projection. So you could start with 2, -7, 5, and you can project that into the first two coordinates, and that means nullifying the 5, but we have to put an element in its place. So we have now 2, -7, 0. That would be a projection of those three into the XY plane. Yeah, this is related to three-dimensional coordinate systems, and this could be a representation of a point in 3 dimensions, and if we project that point into the XY plane, then we end up with this new vector. But let's not get ahead of ourselves. The point I want to make right now is that this vector and that vector have nothing to do with one another. It is a pure coincidence that we have a 2 and a 2 and a -7, -7. They're not in the same planet. It is coincidental that we have the same first two coordinates. And the same thing is true when we have variables. X, Y, Z is in a completely different planet than X, Y. We can make some kind of projection, but let's, for now, emphasize that they are different. Another notation that we use with vectors is the IJK notation. So if we write this down as, let's start again with 2, -7, 5, we can rewrite this as 2i minus 7j as a polynomial plus 5k. There are advantages and disadvantages with this notation. One advantage is that the letters tell us which one the first one is. The coefficient of I is the first number. Remember, in a vector, we have to be able to tell which one the first element is, which one the second element is, which one the third element is, and so forth. So in this case, The I tells us which one the first element is, and it is the 2. That means we can scramble this around. So negative 7j plus 2i plus 5k is the same vector, because I still can tell which one the first element is. The first element is 2 because the I tells us which one is the first element. The second element is negative 7. The third element is 5. So this is another notation that we use. People use that notation extensively. The only thing to remember when we're using that notation, let me bring back the example. It is 2i minus 7j, 2i minus 7j plus 5k versus 2i minus 7j. Somebody could ask, well, this vector has nothing to do with that vector, and that is one thing that is different when we use this notation. This notation, ijk, assumes there are 3 parts to the vector, and if one of them is not written, we assume that part is a 0. So indeed, this is a projection of that, which sort of seems to contradict what I said earlier, that 2 comma negative 7 is not at all related to 2 comma negative 7, 5. They're not related. Here, I am saying they are somewhat related. This is indeed a projection of that because we are assuming there is a 0 here. So those two are not the same. They're not the same. Those two vectors are not the same. This is 2, 7 in a 2-dimensional space. Well, this is a 3-dimensional vector that has, well, let me rewrite it again, 2i, so that this guy is equal to minus 7j. And if we don't put the k, that implies that the third coordinate is 0. And the same thing can happen to the first coordinate or the second coordinate. If one of them is missing, we assume that coordinate is 0, and we're assuming that whenever we use ijk coordinates or ijk notation, we have a 3-dimensional vector. A lot of people use an arrow on top of the letters. If it's understood that we are using vectors, then I personally don't see the need for that. Personally. Okay, so let's continue talking about projections. If you have a vector 2 comma negative 7 comma 5, that is a vector that is 3-dimensional, and we can project into the xy plane by causing this to be 0. So 2 comma negative 7, 0 is a projection of this vector, the original vector, into the xy plane. So this is a projection into xy plane. If we set the first coordinate instead to be 0, 0, negative 7, 5, that is a projection of the original vector into, so this is a projection into, so the x is 0, so we have yz into yz plane. And of course, if the middle element is 0, then we have a projection into xz plane. Yeah. All right, so that is, we will talk more about projections when we see the geometry of vectors. Let me talk about vectors a little more, about their notation. And vectors is a big topic, so it is hard to go too sequential on vectors. Some people use different notations for vectors depending on what they do. So for instance, some people use this kind of symbol, -7, 5. Or some people use this symbol, the parenthesis, to -7, 5. And there may be some other ways of writing vectors. I'm going to stick with this notation, with the parenthesis notation. And I'm going to talk more about why some people have different notations within the topic of vectors. So let me give you somewhat of an analogy. If you have the line, rather the equation, y equals 2x plus 3, we know which one the slope is and which one the y-intercept is. So of course the 2 is the slope, and the 3 represents the number of the y-intercept. All right. So again, if you have this equation, y equals 2x plus 3, you know which one the slope is, the 2, and the y-intercept would be the 3. So the question is, if I just write down a number at random, say 5, without any context, can anybody tell me what this is, whether this is a slope or a y-intercept? So the question is it, is it slope or y-intercept? Question mark. Which one is it? This is the 5. And without context, we cannot tell what it is. The context, as up here, tells us what it is. So if we have y equals 5x plus 7, well, then the 5 represents a slope. But if you have y equals 4x plus 5, then the 5 represents a y-intercept. So without context, we cannot tell what the 5 represents. Vectors are a little bit like that. The context of the vector oftentimes tells us what it represents. A vector by itself is just like a number, like the 5. And whether a vector represents a direction or something else, or a motion or something else, the context will tell us what it represents. A vector by itself is similar to a number. And we should think of vectors a little abstractly as we think of numbers. When we say 5, I don't have to tell you that we have 5 apples or 5 pencils. It is clear that we understand what 5 represents. We have the abstract idea of 5. And by the way, 5 could mean a quantity, such as 5 apples, 5 chairs, but it can also represent a magnitude. It can represent many things. And vectors are similar to that. They can represent many different things depending on how we apply them. And we should think of vectors a little bit in the abstract. It is easier to go down to the applications if we understand the abstraction. Having said that, there is the other way of thinking. If we have enough applications, then we can understand the abstraction. So there's two ways to think of vectors. Mathematics in general, we can start with many applications, go into the abstractions, and then, or we can start with the abstractions and then go to the applications. Both are good. But let's move on with addition of vectors. So how do we add vectors? Well, we can only add vectors of the same dimension. Vectors of different dimensions live in 2 different planets. They cannot be really put together. But if they're of the same dimension, then we can add vectors. So addition of vectors, let me change pens, occurs component-wise, is performed component wise. So if you have the vector 2, 3, 4, and we add to the vector 5, 0, -7, then we end up with a new vector, which is going to be 2 plus 5, 7, 3 plus 0, 3, 4 plus -7, -3. So this is the vector resultant of adding those two vectors together. The addition of vectors, hence, is inherited from the addition of real numbers. So because we have an addition with real numbers, we can add vectors using that addition element by element. That is important to know. In the vectors where we have furniture, for instance, or names, there is no addition of furniture. A chair plus a table, we don't know what that would be. You know, if you have, let me start with the numbers. 2 plus 5 is equal to 7. We know exactly what it is. It is well defined. We've done this since we were in elementary school. But if you have a chair and we add a table, how are we going to add that? Somebody could say, well, let's just express it as the addition of a chair plus a table. But is it going to give us another piece of furniture? Is it going to give us, are we going to take the chair and the table apart and put it together as a third piece of furniture? Or it's not clear. Same thing if we have two names and we add the two names. If we add Mabel and Betty, for instance, are we going to end up with a new name? You know, it's Mabel plus Betty. Is that going to be what? Mabel Betty? I don't know. What is it going to be? We haven't defined what we mean by the addition of two names. However, the addition of two real numbers is very clear, and consequently, we can define the addition of two vectors as long as the vectors are exactly of the same dimension. We also have to be able to tell which one the first element is on each one of the vectors, because when we add the vectors together, we have to add them component by component. We cannot add the first coordinate of this vector with the third coordinate of the vector over there. That's not going to work. So there. What I'm trying to say is that the addition of vectors is completely a ramification of the addition of real numbers. In this case, the real numbers in this case is going to also be called this scalar set. So by scalars, we mean are elements of the real number set. Yeah. The reason why we have the real numbers is because the vectors we're going to be working with are real number vectors. If we had furniture vectors, then the scalars would be the furniture. But with furniture, we don't have operations that we can deal with. So we don't call them, we don't use the furniture as scalars, of course. The reason why we need to emphasize that we have real numbers is because now we're going to define the multiplication by a scalar. So multiplying a vector with a scalar. So that means with just a number. So if you have the vector 2, comma, -7, 5, we can multiply with any scalar, that means with any number, say 3, and that will give us a new vector. And it is pretty expected that what we're going to do is multiply the 3 with each one of those components. So we're going to end up with 6, -21, and 15. And that's the way we multiply a vector with a scalar. We can also factor any scalar from a vector. So this goes both ways. If we have this second vector, we can factor out the 3. And as long as we have the 3 and this 2, -7, 5, that is going to be exactly the same as this vector. We're not going to distinguish between one and the other. And that is handy because if something is too repetitive on the components of the vector, we can factor that out, and then we don't have to rewrite that same factor many times. By the way, a vector doesn't have to be a 3-dimensional. It can be 4-dimensional, 2-dimensional, 4-dimensional. Any natural number of dimension is allowed in a vector. Let me go back to direction, motion, and position. So direction, motion, and position. A vector can be used for any of those three. It can represent a position in space. It can represent a motion. It can represent a direction. And it can probably represent many other things, but we are mostly interested in the representations of vectors as far as directions, motions, and positions. We're not gonna rewrite vectors differently depending on what we have, because the context should tell us whether we're looking at a vector from a position point of view, or a motion point of view, or a direction point of view. Yeah. An analogy I want to provide is this. If you have 4 plus 5, and we look at this on the number line, there is 0, 4. Okay, so we start with the position 4. So this 4 represents position. And then we're moving 5 units to the right, 5 units this way. And that gives us a new position, which is 9. So one way to think of this is the first number starts with the position 4. We move up from 4, 5 units, and we end up with a new position. Let me squeeze that in here, which is 9. So we're using numbers differently. Somebody could say, well, wait a minute. You could think of 4 as moving from 0 to 4. Sure, we could. Yeah. Or we can think of 4 as starting at 4 and then moving up 5 units. It's clear, though, they're different, though, because in this equation, in this operation, we're moving 5 from the 4, from the position of the 4. We're not moving 5 from 0. So even with regular numbers, with simple equations, we think of the numbers differently depending on where they are. And of course, because of the commutative property, we know that this is the same thing as 5 plus 4. But then we start with the 5. Let me draw this again. So we don't start at the 4. We start with the 5, a little bit to the right. And then we add 4 on top of that, and we end up with the same 9. So we move 4 units to the right. So it is good to understand that vectors are like numbers, which can be used in different ways. They can be used to represent position, motion, direction, and so forth. Yeah, let's elaborate on this. So as a position, let's talk about vectors as position. All right. Well, if you have the vector, I have to change vectors now. My example of 2, -7, 5. Well, I guess we can keep that one. So 2 means 2 units this way. -7 means 7 units to the left, and then 5 units up here. So this is the vector 2, comma, -7, comma, 5, the position. But somebody could think of it, wait a minute, that's actually the motion to go from 0 to this point. And oftentimes people draw an arrow indicating or emphasizing that we're moving from the origin to that point. Sure, we could do that, just like with 4 + 5 = 9. The 5 could mean moving from a certain position up 5 units. So we can think, again, this vector could represent this location relative to 0 by going 2 units in the x direction, 7 units on the left of the y direction, or the opposite of the positives, and then up 5 units. So x left up. Or it can represent the motion to go from 0 to here. Now, one problem with that is that we can think, well, wait a minute, but there's more than one way to go from 0 to here. You can move 2 this way and this way. In fact, it is true that 2, comma, -7, 5 is equal to 2, 0, plus 0, -7, 0, plus 0, 5. So it is true that we could, but then, see, we're already getting into, are those 3 together the same as that? Yes, as a result, they are the same. Is it the same motion? See, that's when we get into ambiguities or contradictions. Well, moving this way results in the same final location as moving this way. And direction. So the direction could mean going from here that way, this way, regardless of how far the endpoint is. So the direction to -7, 5 could be the same as the direction, so same direction as the same vector, but half the way. So 1, comma, -3.5, comma, 2.5. Oops, my 5s are sometimes not very clear. Sorry about that. Is a vector that is half the length as the original vector, half the length. This one, 1, -3.5, 2.5 is in the same direction, but it has a different length to it. It is half the length, because by halving each one of the coordinates, we are ending up with half the vector. And by half, we mean same direction, half distance between the origin and the final vector. We could also multiply by 3, or so same direction as this, or we can multiply by 3 and end up with 6, -21, and +15 will be in the same direction as our original vector, but 3 times as long. It won't fit. Well, it may not fit into this piece of paper. So So we have position, motion, and direction. Yeah. Now, those are only three different ways to think of vectors. There are many, many ways of thinking of vectors. It is not good to think of mathematical concepts in only one way, because we think we want to think abstractly. The analogy that I think of is like thinking that a number is only used to represent amounts of money, like $5. But numbers can be used to represent other things: 3 pens, 4 chairs, 5 people. So, and yet we don't have a problem with the concept of number. Number can represent many things. And similarly, we want to think of vectors as sort of numbers, which can represent many things. They can represent direction. They have a magnitude. And they can represent location and so forth. All right. An interesting vector is the opposite vector. Opposite vector. So if you have a vector, 2, -7, 5, its opposite versus -2, +7, and -5 can be found by multiplying by -1. So if we do -1, the scalar -1 multiplied with the vector 2, -7, 5 gives us the opposite, which is -2, +7, and +5. So that is the opposite vector. We also have the zero vector, which is in 3 dimensions, 0, 0, 0, and we oftentimes represent it with a big 0, or a small 0, or just a 0. Again, technically speaking, well, some people put an arrow on top of the 0, indicating that we have a vector that is 0, but then I feel that if we do that, then we have to also state the dimension of this 0. So to avoid complications, I usually just write a 0. And again, the context tells us what kind of 0 we have. So I have to admit, this is confusing, because is it the single 0? So is it scalar 0, or is it vector 0? Question mark. When we are talking about vectors and you see a 0 showing up in some kind of equation, the question could arise, well, what do we mean? Do we mean the vector 0 or the number 0, the single number 0? And I believe most of the time the context will tell us what we have. So I don't mean to jump back and forth, but let's say you have the vector 2, -7, and we add its opposite, which would be -2, 7, we end up with a vector 0. Technically speaking, we can rewrite it as 0, 0, but oftentimes we write this as simply 0. And we mean this is a vector because we are adding 2 vectors. And when we add 2 vectors, we end up with a vector. So this is the vector. I'm gonna get a lot of feedback, not necessarily good feedback for that, but I hope it is okay. So that is the zero vector. Oftentimes we want to add the opposite of a vector. So instead of adding -1 times the vector, instead what we do is write minus. So 2 comma -7 minus 2 comma -7 means multiply the second vector by -1 and then add the first vector to the result of multiplying the second vector by -1. So in this case, we end up with 0 as we expected. Yeah. We call that subtraction. This is the subtraction of two vectors. So the subtraction is really an addition where the second vector that we're subtracting is the result of, I'm sorry, let me go back. The subtraction is the addition of two vectors, the first vector plus the multiplication of the second vector with -1. We have many properties of vectors with their operations. Let's write some of those down. Properties of vectors. Addition of vectors is a commutative and associative. Associative. So those are the two first properties of vectors. Those two properties are inherited from the same properties of real numbers with addition, because the addition is commutative and associative, and consequently, those two properties carry over to vectors. There is a zero vector. There is a zero vector. And let's understand what the zero vector does. If you have any one vector, A, B, C, any three-dimensional vector, and you add with a zero vector, 0, 0, 0, we end up with the first vector every time. So what is relevant about the zero vector is that it neutralizes the addition. It doesn't change the first vector by adding the zero vector. That is an important property of the zero vector. In fact, it is also called the identity of the addition of vectors, because it keeps the original vector, the first vector, intact. Every vector has an opposite. So if you have A, B, C, there is another vector, namely -A, -B, -C, that gives us the neutral vector, the zero vector. Yep. So we have an operation that happens to be commutative and associative. We have an element that neutralizes that operation. And then we have, for every vector, an opposite that gives us the neutral element corresponding to that operation. So there's a chain of concepts that are built on top of the other. In order to talk about zero, we have to have an addition. In order to talk about opposite, we have to have a zero. And the operation that we deal with should be both, well, associative. It doesn't have to be commutative, but for sure, it should be associative. In this case, of course, since we're talking about real numbers, the operation is commutative. There's other properties, distributive properties. So the one here, the number 3 property, is the existence of 0. This property talks about the existence of an opposite for every element, for every vector. We have distributive, so if we have x multiplying a BC plus the EF, the sum of 2 vectors. So we're going to put this in brackets. So we add 2 vectors. Whatever the answer is, we multiply by x, by the scalar x. That is the same thing as multiplying the x with each one of the vectors, a, b, c, plus x times d, e, f. And we can use this equation in both directions. We don't necessarily always distribute. We could factor instead. Yep. So that is the distributive of a scalar over the sum of 2 vectors. But we can do the other way around. We could have 2 scalars, x plus y, multiplying a single vector, a, b, c. And that is the same thing as multiplying each one of the scalars individually by the vector a, b, c plus y, a, b, c. So we can distribute as a single scalar over the sum of 2 vectors, or we can distribute a vector over the sum of 2 scalars if we're multiplying, if we are applying scalar multiplication over a vector. It can get a little confusing at first, so it is a good idea to do a bunch of those examples if you can find them somewhere, practice and multiply. When we have operations such as scalar multiplication, we want to make sure that the operation is consistent with the multiplication of real numbers. So we have another property that says that if you have, let me flip this over there. 2 scalars multiplying each other, say x, y, with a vector, a, b, c, we want to make sure that there is no ambiguity as far as how this is going to be multiplied, in the sense that should we multiply the y with a vector, giving us a vector, and then multiply the x with the new vector, or should we multiply xy first and then multiply with the vector? And it turns out that it doesn't matter. We want to, this scalar multiplication and regular multiplication of scalars is associative in a way. So it doesn't matter, again, whether we multiply the x and the y together first, and then we'll multiply with the vector, or multiply just the y with a, b, c, and then after multiplying that, multiply with the x. Either way, we're good. The number 1 in the real numbers multiplied with any vector, a, b, c, is of course going to give us a, b, c. So 1 works as an identity element for vectors, for scalar multiplication of vectors. Just like 0 is an identity for the addition of vectors. The 0 vector is an identity for the addition of vectors. All right. Let's talk about geometry for a moment. If we have a vector A, and a vector B somewhere, oftentimes we want to find the vector that goes from A to B, as if this was the origin. What we could do is just, let's say the origin is here. Origin is there. We can anchor the whole space to the origin. We can shift, that's what I mean by anchoring. We can shift the whole space so that A becomes the origin of the whole space. And we can move every point in the same way. So if A is moved to the origin, and we move B in this exact same way, then we end up with B without starting with A, starting from the origin. So we have this vector. Those two are the same vectors in the sense that they have the same components. Yeah. So let's say you have, another way to think of that, by the way, is if you start with A and then go to B, the way to find A to B is to subtract B minus A. Yeah. So this vector, which is the same as this vector, is B minus A. B minus A. Yeah. It's similar to numbers when you think about it. You know, you have 0, 4, 5. Well, 9, how do you know what distance you travel to go from 4 to 5? Well, you do 9 minus 4, which is going to give us 5. So we can think of 5 as this guy from 4 to 9, or we can think of 5 as this number here, from 0 to 5. So both are 5s. This is on top of the 4, and this 5 is from 0. Similarly, this vector B minus A is starting with A, and here it starts from 0. So think of vectors abstractly rather than with one particular application. They can be used differently. Magnitude. Magnitude is the same thing as distance to 0. And we covered this in the previous video, but let's go over this again. If you want the absolute value of a number, algebraically, you can achieve this by taking the square root of the square of the number. So first, square the number, that gets rid of the negatives, if there's any negative, and then take the square root, and then you end up for sure with a positive number. By the way, this symbol means the positive root, positive square root. If you have a vector A, B instead, then its magnitude will be the square root of A squared plus B squared. And if you have a vector A, B, C, its magnitude will be the square root of A squared plus B squared plus C squared. And you can do that with 4 dimensions, 5 dimensions, etc. So we have a nice, neat pattern going on here where we square. So that is the magnitude. Our friend, our old friend 2, negative 7, 5, let's find the magnitude of this vector. So that will be 4 plus 49, because we squared the negative 7, plus 25. So that is 74, 78. That is the square root of 78. Yep, 39, 13.3. See, we cannot simplify that. So that is the exact magnitude of this vector. And if you multiply this magnitude by 3, for instance, or this vector rather by 3, So if you have 6, -21, +15, this new vector, not the same vector, this is 3 times as much as that vector, the magnitude will be 3 times square root of 78, because what will happen is that the 3 embedded into each one of these terms, coordinates, will be squared as a 9. So sure enough, this is going to be 36 when we put that into this formula. And 21 squared, I have to figure that out, 400 and change, I believe, and then 15 squared, another bigger number, 200 and change. And but then we could factor the 9 out inside the root, and then we can move the 9 out as a 3, and that's how we would end up with 3 times the square root of 78, assuming that my 78 is correct. Okay, we have a vector, a special vector, that has exactly the same direction as those two, but whose magnitude is 1. And that vector is very, very neat. It is handy because it only gives us direction. It doesn't give us anything else but direction. That is called the unit vector. So the unit vector associated with those two vectors, it doesn't matter which one you pick, we're going to end up with the same thing. So the unit vector is the one with the same direction as those two, but with no magnitude. And by no magnitude, we don't mean 0, we mean 1. A magnitude of 1 that does not change any other magnitudes by multiplication. So the unit vector associated with those two, let's start with the simplest one, this one. If we divide each one of those by the square root of 78, we end up with 2 over the square root of 78, comma, -7 over the square root of 78, comma, 5 over the square root of 78. That is a unit vector with exactly the same direction as those two vectors, but with a length of 1. As you can tell, here's where factoring out or the scalar multiplication is handy, because this is quite repetitive. If you have big things happening repeatedly over the vectors, it's simply easier to just do 1 over the square root of 78 once, and then just put 2 comma -7 comma 5. And that is simpler than writing the square root of 78 3 times. Okay. Let's stop the video here. There's an example coming up, but I'd rather do the example in a new video. So I'm going to stop the video here.